Hi, this is Bob Wells here, and welcome to Undercurrent Stories. This is the show where we hear about people's interests and uncover some fascinating stories at the same time. I hope you enjoy today's show. When you think of a volcano, you tend to think of a mountain with a crater at the top, sometimes with smoke seeping out and occasional eruptions, sometimes with devastating consequences. But what exactly are volcanoes? How and why are they formed? What causes them to erupt? Well, here to answer those questions and many more, I'm delighted to be joined by Tamsin Mather. Tamsin is a volcanologist, an atmospheric chemist, and Professor of Earth Sciences at the University of Oxford. Her work is helping to predict when a volcano may erupt, and also the influence they have on our planet. She has just published her first book, Adventures in Volcano Land: What Volcanoes Tell Us About the World and Ourselves. Hello and welcome to the show, Tamsin.
Hi there.
Thank you ever so much for coming on the show. It's really great to have you on. Before we talk about volcanoes and your book, could you just tell us a little bit about yourself, your life's journey, and how you sort of became interested in volcanoes?
Well, I actually became a volcanologist somewhat by accident, which probably sounds a little bit strange. Many of my colleagues have been completely obsessed with volcanoes since they were young children. And I certainly, if I look back on it, actually, there are lots of strands that come together. So I went to my first volcano aged 10. I talk about that a bit in the book. That was Mount Vesuvius in the Bay of Naples in Italy. And we visited Pompeii and Herculaneum, which are two of the sites that were overwhelmed by the AD 79 eruption of Vesuvius. And I do distinctly remember that making quite an impression. And when I came to writing the book, actually, it brought back a lot of memories of that first visit. But I loved science, I loved maths at school, and then went off and ended up doing a chemistry degree at university, and then took a couple of years out of science. And during those couple of years out of science, I decided I wanted to go back into using my chemistry, but to not just be in the lab. I like doing lab work, but I'm also always been very passionate about being outdoors, about nature. And so I thought, wouldn't it be amazing if I could combine that passion with doing my science? So initially I was looking at kind of ocean chemistry PhDs because I'm a very keen sailor, very, very, very inspired by the sea. And then when I was applying for University of Cambridge, it was a booklet of projects. It was actually a real booklet in those days. You had to send off for it. None of the download from the internet stuff we're able to do these days. But I was asked to put a second choice project down. And I was looking through all these projects, and having come from a chemistry degree, I didn't recognise half the words in these project titles. There were all these wonderful mineral names and things like that. And then I saw this project title, which was the tropospheric chemistry or the atmospheric chemistry of volcanic plumes. And I'd actually done a specialist module in atmospheric chemistry in my undergraduate degree. So I put it down because I understood all the words in the title. And then I met up with the supervisory team when I went for the interviews and just got completely inspired. So when they offered me the PhD, I asked if I could switch to the volcanoes. And the rest is history, as they say.
That's fascinating. And it always fascinates me how somebody like yourself can get into a subject. And you're almost like a lifelong learner. You're continually learning about your subject. So if you look at it on the surface, literally, a volcano, like I said at the beginning, it's a mountain that erupts, sometimes at sea and all the rest of it. But, I mean, you're learning new stuff all the time, aren't you?
That's part of what I love about my job. And actually, it's part of what I love about volcanoes as well. So I started off in my PhD looking at the gases that come out of volcanoes and the impacts that they have on the environment in quite a local area around the volcano. And since that time, so my PhD was about 20 years ago now, I'm embarrassed to say. It seems to have gone by in a flash. I can't believe it. But actually, since that time, I feel like I've gone outwards and inwards. So I sort of started on the crater rim, if you like. And then since doing my PhD, I've sort of delved a bit more into thinking about the subterranean processes going on in volcanoes. So things about like what's going on in the magma storage area and how we might tell that from surface signals, what's going on in hydrothermal systems underneath the surface and things like that. But also sort of gone outwards to thinking about the global effects of volcanoes, volcanism as a planetary scale process, so not even just a single volcano, but all the volcanoes in the world, and the effects they have when you add up all of their emissions over geological time. And even actually ended up thinking about volcanoes on other planetary bodies as well. So it is very exciting. It's part of what I love. And I'm just starting a new project now, thinking about volcanoes and their potential to provide us with critical metals.
Wow.
And that's not quite starting at square one, but there's a whole bunch of new chemistry I've got to get my head around about salty fluids at high temperatures and pressures. And I just need now to find a little bit of time to sit down with my textbooks and notebook and try and work it all out.
It sounds ever so interesting. So for myself and the benefit of listeners, are you able to sort of give, I'm sure you are, but could you give a brief summary of what a volcano is, please?
Well, a volcano is where a magma, so that's a liquid, and normally on Earth it's a liquid silicate rock, so a rock that's dominated by the elements silicon and oxygen, comes up to the surface and then erupts. And so I guess we're most familiar, as I say, with Earth's volcanoes. So we often think of a volcano as a mountain, and that's because often this process of erupting magmas builds up mountains. But actually, when you think a little bit further about it, and you think about the volcanoes you've maybe visited or seen on television, they're not all mountains. Some of them you get like the ones that we're seeing in the Reykjanes Peninsula in Iceland just these last few years. They are cracks in the ground that open up, and then you get fire fountaining, which is spectacular, or curtains of fire, which is where you have the scoria, the red hot scoria flying out. Then lava flows flowing away, and it builds new surface. It builds new surface to the planet, but it doesn't really build an edifice, a mountain as such. And then, of course, some of the very largest eruptions actually give us enormous, enormous craters. So these we often call calderas. But if you look at aerial photographs of Yellowstone or Santorini in Greece, which is where we talk about some of these processes in the book, but actually it's an enormous crater because the volcano has emptied out the magma storage zone in the shallow crust, and then the crust has caved in and given us this big depression in the ground. So what is a volcano is quite a profound question, really, but sort of fundamentally it's where magma finds its way to the surface. But I also sort of see that often the word volcano conjures quite a specific image in people's minds.
Magma, you mentioned something about silica within it. Is it always the same bunch of chemicals?
No, not always at all. I sort of drew my lines quite carefully in the previous answer because even on Earth, they're usually silica-based magmas, but we have some really unusual volcanoes. So Odonia Lengai in Tanzania, for example, actually erupts carbonate-based magmas. So the liquids that come out and solidify are a bit more like, sort of washing, they're carbonate-based, so sort of very, very runny, and a bit of a different kettle of fish altogether. But on other planets or other icy moons, we can also get ice-baked, we call it cryovolcanism. So you actually have water or liquid methane coming out of volcanoes and solidifying on the surface.
What exactly is lava? Is it dried magma?
It's not dried, but yeah, solidified. It sort of seems a bit that way, doesn't it? No, so the magma comes out of the volcano and it's hot and runny and liquid. Yeah, and then it freezes. So okay. It's just like it's a similar process to water turning into ice, but obviously at very, very much higher temperatures.
My sort of understanding of a volcano and the magma was that we've got a molten center of the Earth, and you've got all this stuff. I'd say boiling. I don't know whether boiling is the right word, but heating up at a fantastic temperature, and it has to have somewhere to go. So it comes up through the Earth. Oh, look, there's a mountain there. I'll come out through that. How true is that?
It's not. It's interesting. That's sort of one of the stages we went through in understanding our planet, and I do sort of see that represented sometimes in, picture books about volcanoes, for example. But it's not our best scientific understanding these days. It's all a bit different. So the Earth, you're quite right that the Earth has layers and it has an inner part or a core. So we do have a liquid outer core and a solid inner core, in fact. but it's very, very, very deep. And most of the Earth is solid. So most of the Earth, we live on the crust, and the layer below is called the mantle. And most of the Earth is this solid mantle. Now, it's solid, but because the pressure and temperature are so high, it kind of behaves in a bit of a different way to how we're used to solids behaving at the surface of the planet. So it's able to creep very slowly, this solid. So it's actually able to move and flow, but on very, very slow timescales. So the timescale of mantle flow is about the same timescale as your fingernails grow, just to give you a reference point.
Yes.
And what causes most volcanoes on our planet, or the volcanoes on our planet, is where the mantle melts. So we get these different scenarios. I'll go through some in a second, where you get partial melting of the mantle. So it's like you've got the solid, and then it's almost like these little droplets of liquid start squeezing out of it and finding their way up to the surface, and that's what causes volcanoes. And there are differences. It all ties into the theory of plate tectonics, which since the 1960s has really given us this incredible understanding of how our planet works in total. So I guess there are three main places we get the melting mantle, which then gives us volcanoes. So that's where two tectonic plates are splitting apart. So places like the Mid-Atlantic Ridge. So Iceland is a very famous example of that.
Yeah.
And it reduces the pressure on the underlying mantle, and that changes its melting point and gives you magmas. Then another one is subduction zones, where you've got one tectonic plate sinking under another one. So the Pacific Ring of Fire is a really good example of that. So think the volcanic zones in Chile and Ecuador and places like this. And there you have the tectonic plate sinks, and that actually pushes water and other things off that downgoing plate. It changes the chemistry of the mantle, a bit like sprinkling salt on your driveway in the winter. Changes the melting point, and you get magmas. And then the third main one is hotspots, and we just have this hot upwelling from deep, possibly as deep as the core mantle boundary, deep upwelling of material from deep within the planet. And the hot material comes to lower pressure, partially melts, and you get volcanoes. And Hawaii is a most excellent example of that type of volcanism.
And what type of temperatures do what type of temperature does the magma get to just before it erupts?
So it varies depending on the type of magma, but the basaltic magma. So when you melt the mantle, you get basalt in the first instance, and then it can change chemically. I talk about that in chapter 2 of the book about how that might happen. But the basaltic magmas are about 1,000 degrees Celsius.
Wow.
Yeah, it's pretty hot.
Yeah, it is, isn't it?
I know. I stood up close to basaltic flows, and you can really feel that heat. It's quite incredible when you stand close to a lava flow and you just lean in a tiny bit, and it is absolutely searing. And you realise if you stumbled even a metre closer, you'd be in real trouble.
And when you say close, how close?
So I guess I was a few metres away, standing on one of the levees, which are these sort of trench, these little walls that you get building up on the edge of a lava flow. The time I'm thinking about is Mount Etna in 2006. It was awesome.
Right. One of my friends who I spoke to about the interview that we were doing asked me a question. He said, "What does a volcano when it's erupting smell like?"
Oh my goodness! Yeah, well, this is very much my thing. The gases coming out of volcanoes. So yeah, it's I mean, if you're really getting a mouthful of it, you should probably have a gas mask on.
Oh, really?
But yes, but on the other hand, sometimes you're approaching and it's pretty hot work in a gas mask to take it off. But it's often a mixture of the main things that smell in a volcanic plume are the sulfur species, sulfur gases. So there's often a mixture of this kind of metallic, rasping, burnt matches smell that you get from the acidic sulfur dioxide, probably added to by the acidity of the hydrogen chloride and hydrogen fluoride and other nasties that you've got in the volcanic plume. And then sometimes you'll also have this rotten egg smell, which is the hydrogen sulfide, so H2S, that's coming out as well. So I guess that's often the main smells that you get.
Yeah, I guess the sulfur. But the other thing we were talking about was, is it anything like, after a firework goes off?
No, not so much, because it's not really smoke as such. It isn't burning. It's just these gases being released from the magma. I guess sometimes you do get, I wasn't there, but one of the recent Icelandic eruptions, you got quite substantial moss fires as well being triggered by the lava flows. So you can sometimes have burning vegetation that then can contribute to the experience.
You've obviously done quite a bit of field research. It's a big part of your job. I mean, field research, it's getting near a volcano, going up the mountains and all the rest of it. Could you just describe what that sort of research, the field research, entails?
Well, there's a huge variety of different things that we're often doing. And each chapter in the book has at least one field trip in it and a bit of a description of what we're doing there. So sometimes, sometimes it's a matter of getting the equipment into the gas, into the volcanic plume. So we'd only do that if it was as safe as possible to do so. So you normally go for very low explosivity eruptions or activity for obvious reasons. So you're often carrying quite a lot of heavy equipment up a volcano. So Mount Etna, for example, we drive as high as we possibly could, but then it's still about an hour's hike carrying car batteries and pumps and the sampling equipment and things like that as well in order to sample all the chemical components of the plume. If we're very lucky and we've chosen our volcano well, like Masaya volcano in Nicaragua or Kilauea volcano in Hawaii, you can pretty much drive, or you can drive, into the volcanic gas. Wow. And that obviously makes life an awful lot easier. It means you can get a lot more experiments, a lot more measurements done in a much shorter time because you're not having to carry everything there. You can do multiple experiments in one day. But those are quite rare volcanoes where you can actually drive the equipment into the plume itself. But other times, we're not actually working in an active volcanic environment at all. We're out in the environment sampling the products of old eruptions, for example. So going around and looking for ash layers in soil profiles and things like that. Or measuring the carbon dioxide seeping out of the ground around volcanoes. So there's a whole range of different activities that we get up to when we're doing field work. It really very much depends on what question we're trying to answer.
And typically, how many people would be in your team to go along to?
And that again really varies a lot.
Yeah,
but sometimes you've got a big consortium of scientists on a particular volcano for a particular reason. And that's always quite interesting because it becomes you have to work out. Everybody will have different objectives, and you've got to kind of manage that as well, especially if you're one of the more experienced scientists there. So you might have a team of different PhD students and you have to coordinate to make sure they all get the measurements that they need and want. And other times it's just very small groups. I mean, I've worked sometimes with just one other person for a couple of weeks. And we're just doing our thing, climbing the volcano every day that we can and doing whatever experiments we can. So there's a real range there.
You must have visited many countries. I mean, have you ever sort of taken a sort of count of how many volcanoes that you've been to?
No, I've never done that, actually. I probably should. I think that if I did that, I'd probably just get very, very... I'd probably have a longer list of ones I want to go to than ones I have.
Do we know how many volcanoes there are on the planet?
Yes, there's a catalogue, the Smithsonian catalogue. So these are all the ones that have been active in recent geological time. So yeah, you can look that up on the internet. It's many hundreds to 1,000.
Is it?
That have been active.
And you were talking about historic volcanoes that are no longer. Here in the UK, do we have any old volcanoes?
Yes, very, very old volcanoes. But Arthur's Seat is a very famous one up in Edinburgh. That's an old volcanic structure. And actually, I do talk about for example, the volcanic deposits on the island of Skye feature in the book up in Scotland again on the northwest coast. So we absolutely, and Lundy in the Bristol Channel. There's lots of remnants of volcanism in the British Isles, but yeah, nothing that's going to be active. We're in a tectonic backwater just for now.
Are we? That's
But
probably cool.
the deposits on Skye are very interesting because they're part of one of these large igneous provinces. So it's the North Atlantic igneous province, and so when when those lavas were being erupted, there was an enormous outbreak of volcanism in the general area over a prolonged period of time, and that potentially triggered global warming. So there was a sort of what we call a sort of climate maximum, where the carbon dioxide levels in the atmosphere got to much higher levels and caused global warming. So that's one of the sort of episodes in the planet's past where volcanism's really had a profound environmental effect, and there's lots of feedbacks as well. So it's not just the volcanoes.
And on going back to your field trips, have you ever had any surprises or made any discoveries with some of the research that you've been doing?
Yes, that's always a very exciting moment. I'm just sort of thinking of, well, is it a good example is thinking about actually when we were in Nicaragua and Messiah volcano. So we had a hypothesis. We had an idea that the hot lava lake, which was down the volcanic vent at that time, might take atmospheric oxygen and atmospheric nitrogen, heat up to high enough temperatures for the two to react and to get what we call fixed nitrogen. So actually biology needs nitrogen. There's loads of nitrogen in our atmosphere, but most of it's unavailable because it's in this chemically inert gas form. So some processes like lightning, leguminous plants fix nitrogen and make it available for biology. So we had this hypothesis that maybe volcanic heat could do the same thing. And the hypothesis, this isn't terribly important on the present day planet, but if you go back in geological time before we had biology, you wonder why you've got fixed nitrogen that biology needs. It's a bit of a chicken and egg thing. So we had this idea, and we sat in the car park, the gassy car park at Messiah, for the whole afternoon and watched the volcanic plume happily lofting over our heads. So we weren't measuring any gas at all. Didn't have our gas masks on. It was a pleasant afternoon, but we were getting no science done. And then as the evening came in and the sunset, everything cooled down. The plume started settling over us. We started getting these really, really cool measurements showing that we had fixed nitrogen, so nitrogen oxides in the volcanic plume. But then it was time to pack up and go home. So that was a pretty exciting moment. When I plotted out the data at the hotel that night, I saw this spike. And we were tracking the particles so we could see that we could prove the plume had come down and we could smell it anyway. So, yeah, moments like that are incredible. I would say we then decided to get up really early the next morning to try and get the pre-dawn plume and measure that because we were really excited about these results. And very ill-advisedly went into the national park before the security guards had arrived. We had good relations with the park people. They were very supportive of our science, so they allowed us through the gate, and then got held up at gunpoint on Messiah's crater rim, which was very traumatic, but entirely our fault because that's the reason that you have the security guards in the national park. So the lesson there is sometimes don't get too carried away with your science.
Check with the authorities first.
Absolutely.
In terms of forecasting when volcanoes are going to erupt and cause devastation, and I know they don't just cause devastation, there are some good points which you mentioned in the book, but we'll talk about that a bit later. How good are we now at forecasting when a volcano is going to erupt so that we can warn people in advance?
Yes, so unlike earthquakes, volcanoes do generally give us clues. They don't always. There's certain types of eruptions that can come on very quickly, and it's very, very tricky to read the clues still. But oftentimes we do have clues that they're going to erupt. So the clues include seismicity. So we have seismometers. Ideally, we'd have them all the way around the volcano so we can get a really good picture of what's going on. And what they can see is very small earthquakes. So you might not necessarily feel these earthquakes. Some of the larger ones you will, but they're not like the big kind of tectonic earthquakes that cause tsunamis and mass devastation that we see on the news. But they're very small earthquakes, and they tell us that magma and gas are moving inside the volcano or inside the Earth's crust. So we could sometimes use that to track where magma's going. So if I take like the recent Icelandic eruptions, for example, they can see the magma moving, they can see the seismicity.
Wow.
And that building up over the weeks before an eruption. They can also see the ground swelling up. It's not necessarily quite like a blister. It can be a bit more complicated like that, but sometimes it can just be like a blister. But they can watch the ground swelling up and they can look for the patterns in that. That also tells us things about where the magma is in the crust. But one of the complexities with the Icelandic eruptions is they know the rough area it's going to come up and they know roughly when it's going to come up. They've made some good predictions. But they don't really get until about half an hour before the eruption. They can't pinpoint the when and the where.
Yeah.
So they can give a prediction in terms of probabilities, but it is still not locked down until that really tight window around the eruption. And I think this is always something I think about. So I think we can often do quite a good job at saying there's an eruption likely within the next 2 weeks or within the next 2 months or even within the next 5 years because we're seeing a volcano reawaken or something like that. But you think about what's useful on a human timescale. What you really want to be able to say is there's going to be an eruption next Tuesday or there's going to be an eruption tomorrow. And that's very tricky to do because we're always just dealing with probabilistic ideas and with a sort of a geological timescale. I mean, it's actually amazing that we're able to say a volcano is likely to erupt in the next 5 years, given the geological history of our planet is 4.5 billion years. And many of these volcanoes have been in existence for many thousands of years. But for humans, our human timescale is just completely different timescale to the way that geological forces operate on our planet. So you think about how you plan your day and your week. You need information in a totally different way to the way that volcanoes are operating. So I think that's part of the challenge. We have lots of new technology and lots of knowledge now that does happen, and there are some really good success stories about where good evacuations have been called. But it's always going to be that timescale problem that we're going to come up against in some ways.
Yeah, and I guess the ones beneath the sea are particularly dangerous in terms of their magnitude if they're big ones, where they can cause a tsunami.
Well, it depends a bit how deep they are. If they're very deep, they tend to be less so. But I guess a very famous example is Krakatau in 1883, and that generated big tsunamis. So the ones Krakatau was an island, and then it sort of destroyed itself in the eruption. And often it's that sinking process of something sinking beneath the waves that can be a wave generator that causes tsunamis, or other times like we believe after the Minoan eruption, the late Bronze Age eruption of Santorini, it's pyroclastic flows flowing into the sea that can cause these tsunamis as well. So the deep sea ones are less dangerous on the whole, but it's the ones on the coasts or in islands that can kind of interact with seawater as they go, if you like, that can cause those sorts of problems.
And are there new volcanoes continually being formed? Yes.
I mean, there's sort of some famous examples of this. It's always sort of something that can possibly happen. So in Paracutin is a famous example in 1943. This is in Mexico. And it's just a farmer's field. A fissure opened up and the volcano built itself up to 100 meters in about a week. So that was unexpected.
Yeah.
It's if you're in certain volcanic areas, these monogenetic cones can spring up. That's what we call a sort of eruption that happens once at a particular location and then might not happen there again. But they can spring up in relatively in new places at different times.
Yeah, I wanted to talk about the positive benefits of volcanoes because if you ask most people, they would look at the devastation that they cause in terms of looking back at Pompeii, even the recent Iceland one with the ash cloud where planes were stopped and all that sort of thing.
And
tsunamis, as we mentioned. What are the benefits of volcanoes? Not just literally now, but what have the benefits been over time, Tamsin?
It's a great question. It's something that I always like to kind of sell them as friends as well as foes. There's loads of different aspects to what you're asking about there. I mean, people often say, why do people live near volcanoes? And yeah, I understand what you're saying. It's sort of like, it's not necessarily an easy or straightforward place to live, but they often do bring very immediate benefits. So tourism, or they change the weather patterns, so you get more rainfall around the volcanoes because they're big mountains, for example. They bring nutrients to the soils because they're throwing out fresh ash, fresh lava, fresh material. So maybe not right up close where the landscape is really devastated, but downwind actually you can get soil renewal from volcanoes as well. So there's a whole bunch of benefits they can bring locally. There's also, of course, geothermal power, which we don't necessarily not everywhere exploits. But
that's going to be one of my questions.
Yeah, Iceland gets about I think it's about 80% of its space heating. So 80% of its heating is from hot water that's been generated by circulating down into the geothermal systems around active volcanic fields. So there's real potential there. Countries like Kenya really benefit from the electricity generated by geothermal, which is associated with their active volcanoes in the East African Rift. Critical, so mineral and ore deposits often have their foundations in terms of magmatism and magmatic processes. And as I said earlier on, one of our projects at the moment is also thinking how we can harvest the metals out of volcanic salty fluids or brines that are circulating within volcanic edifices, and quite take those metals out to use for things like your smartphone battery and all the rest of it. So those are kind of immediate examples in the here and now. But actually, if we think back in our planet's history as well, I think there's a strong case that we wouldn't be here as a species without volcanoes. So, yeah, so I mean, volcanism, magmatism, which is the more general term, it's played a really key role in forming our planet's atmosphere, so the outgassing of the planet. So if you think about, the Earth accreted from building blocks in the solar system, and then it had an atmosphere. Some people think that got blew off in all the processes going on and all the bombardment of that early period. But it had gas locked up in it, and it was by the magmas circulating around that gas was released, and we got this atmosphere that we have now. And of course, that atmosphere has been modified by a whole bunch of things, including biology, of course. But volcanism has played a role in that. So it created the atmosphere, and then it's also played a role in maintaining the atmosphere. And one of the very cool things that I do talk about in the book is this thermostat that volcanism is part of as well, in terms of balancing out our carbon cycle. Now, we hear a lot about the carbon cycle being out of kilter at the moment with all the emissions we're putting out there, and this is absolutely true. It's the best. So that's our best scientific understanding, that we're really pushing the planet out of kilter. Over geological timescales, the planet will sort that out. It's not going to help us as a species. It won't happen quickly enough. But over geological timescales, that carbon dioxide will get pulled out of the atmosphere by processes of chemical weathering and taken back down and stored in the Earth's crust and in the Earth's mantle, and everything will balance out again. And actually, if that process was allowed to just go unchecked over geological time, we'd have no carbon in our atmosphere at all, which would be bad news because we'd be too cold for complex life to really flourish.
Yeah.
So it's actually the constant emission of carbon dioxide from volcanoes plays a really key role in balancing that process out. So there's a global scale balance that has actually kept our planet much more stable than it would have done otherwise without this balancing effect. That's just some of the examples.
Yeah. That last one you gave is particularly interesting in as much as you said, the volcanoes are responsible for putting a certain amount of carbon dioxide into the atmosphere, which gives us the right temperature for life to be able to exist.
Yeah, so I mean, there are lots of theories about life and the conditions that you need for it, and I think that is also stretches our imaginations to try and think of what life could be and what life could be. And now we're seeing more and more exoplanet discoveries. It's really a super exciting time to think about these questions. And I think sometimes it makes my head hurt to try and imagine what it's life, Jim, but not as we know it. But what life might be out there and what extraordinary forms it could take. But we do make these sort of Earth-based assumptions we're bound to about life, and I think one of them is the idea that it needs liquid water. water is an amazing solvent. So if you want to get loads of complicated chemical reactions, which is essentially what we are, we're just a big vessel of complicated chemical reactions. You need a solvent to allow the molecules to move around and interact. And liquid water is a great solvent. So keeping the planet within the bounds of liquid water has been really important, I think, people think to create those conditions.
And what about evidence of volcanoes on other planets, even including our moon?
Well, you can look up in the night sky and you can see amazing evidence of the dark patches on a full moon are ancient volcanism. That's basalt right there.
Is it?
I think it's the most basalt you can ever hope to see with the naked eye in one image. It's quite incredible. But that's very ancient volcanism, billions of years ago, that created those. But we go to other planets and other planetary bodies, and we see evidence of past volcanism on Mars, for example. Mars actually has the largest volcano in our solar system, Olympus Mons, which is like, it's the size of France, the footprint of Olympus Mons. It's absolutely massive.
Yeah.
And essentially it's a we think it's a hotspot volcano, a bit like Hawaii, but with Hawaii, the Pacific plate has actually moved over that hotspot. So you've got a trail of islands if you look at it on the map, and then if you look at the seafloor shape, you see these islands continue to the west of Hawaii as well. And so the hotspot in the Earth's mantle has stayed stationary, and the plate's moved over the top of it and given you this chain of islands. So Mars doesn't have plate tectonics like we do on Earth. So the hotspot's just sat in one place and built up this one edifice. And we also don't have a hydrological cycle on present-day Mars, so it hasn't been weathered and eroded away in quite the same way either, although there's evidence of a past hydrological cycle on Mars. So volcanism on Mars, or major volcanism, seems to be long dead.
Is there any evidence of volcanoes on any of the planets in our solar system still erupting?
Yes. So I was going to come on to that. So actually, by some measures, the most volcanically active body in our solar system is Jupiter's moon Io. So this moon Jupiter is a big old planet. It's got an enormous gravitational pull, much bigger than Earth, and Io sits there next to Jupiter, orbiting around it, and a combination of that incredible gravitational pull of Jupiter, and then also the tug of its some of its sister moons that it's in a kind of orbital pattern with. So it's getting pushed and pulled and tugged, and it gets deformed. So actually, the whole of Io, it's being sort of squashed. So it's a bit like if you have a squash ball or something like that in your hand, and you squash it and let it release, and squash it and let it release, it heats up. And Io is being sort of squashed and released, squashed and released, squashed and released, squashed and released, heats up by frictional forces, the silicate core or the silicate interior of the planet, and then you get these eruptions. And we've actually seen these eruptions. So this is a really exciting moment in 1979 when Voyager 1 went past. And there was a scientist called Linda Morabito who was working at the Jet Propulsion Lab in California for NASA. And she was just supposed to be processing images for navigational purposes for Voyager 1. And she did one of the image corrections that was very routine on one of the images. And suddenly this amazing kind of fountain showed up against the black vacuum of space. It was early in the morning, and she sort of has this account of sitting with this, and I think she immediately knew what it probably was, that it was some sort of volcanic plume coming out of Io. And by the end of the day, I think they looked at it and couldn't think of any other explanation. So these have been imaged many times or several times since. So we actually saw volcanism on another world.
Amazing.
It was. It must have been the most incredible moment.
Yes. This is a really unscientific question from me. This is a person in the street asking the question, but obviously, my with the erupting of volcanoes in Earth, it's withheld from outer space by our Earth's atmosphere. all of the gases and everything don't actually escape into space. Is that the same on Jupiter's moon?
Well, no, actually, I think that's a very interesting question. So a lot of Io's atmosphere gets stripped off by the enormous gravity of Jupiter. So we haven't got, we're not a moon, we're a planet. Our moon doesn't exert that sort of level. We do lose a bit of our atmosphere from space. We tend to lose hydrogen and helium, for example, because they're lower mass, they're lower mass elements. So we do lose a bit of that. Our magnetic field helps us to keep a hold of more of our gassy envelope. But yeah, on Io, the atmosphere tends to get stripped off by Jupiter's enormous mass. So there's some really cool stuff about, like, actually the aurora on Jupiter might be partially caused by Io's volcanism. It's mind blowing.
This is a whole different episode, I think.
Yeah, I think so. It'd be a lot of fun. It's a lot of fun.
Yeah, no, it certainly sounds it. What are you working on at the moment, Tamsin, in terms of what's your sort of latest project or projects that you're working on specifically to the study of volcanoes?
Well, lots of different things. So one of the things that I've been working on intensely for a few years now are these new sedimentary markers of geologically significant volcanism. So large igneous provinces, which I sort of touched on when I was talking about sky.
Yes.
So these are episodes where you get a big plume of material coming up from maybe the core mantle boundary or deep within the Earth's mantle. And it causes these prolonged periods of volcanic activity, so lasting roughly 1 million years, which is obviously a very long time, but not as long for our planet as it seems for us.
Not in the scheme of things. No.
But so these episodes, they kind of essentially like double the rate of volcanism on our planet for about 1 million years, and that doubles the amount, or roughly the amount of carbon dioxide, for example, being put out. And it does there are various other processes that can go on around the edges. It can heat up carbon reservoirs in the crust and liberate those as well. So there's lots of different ways it kind of changes the balances on our planet. And the interesting thing about these episodes is they tend to have a big environmental footprint. So you can see it in the biology sometimes. So if we've got some people have often heard of mass extinctions. So people have often heard of the demise of the dinosaurs, but actually that's only one of what we call the big 5 mass extinction events. And of course, the demise of the dinosaurs, there was the Chicxulub impactor hit the planet at about the same time, and would seem to definitely have played a really, really major role. There was actually one of these large igneous provinces going off at the same time. So that was the sort of background to the Chicxulub impact hitting. So this is the Deccan traps that are in present-day India, these enormous stacks of basalt that you can see. But actually, if we look at the big 5 mass extinction events, we think at least 4 of them actually coincide with these large igneous provinces. So the biggest mass extinction event in the geological record happened about 250 million years ago. So that was the end Permian mass extinction event. And that coincides with the Siberian traps, which are in present-day Siberia, as the name might suggest. And again, one of these, just this period of enormous outpouring of volcanic activity over 1 million years, really kicking our planetary system and triggering different feedbacks. So I'm really fascinated by these events in our geological past. I'm really fascinated by what they tell us about how our planet works. I'm also really fascinated about what it tells us about what our planet might do in the future, especially with us pumping out so much carbon dioxide at the moment. And what I've been doing is developing new markers for volcanism, because one of the sort of challenges is tying together the different timescales. So we've got the timescale of the biology, and we've got the timescale of the volcanoes. You can pick up a rock from Siberia, say, and get a date on it using radioactive decay of certain molecules within the rock. But you have a big error bar on that. You always do. You're looking at something that happened 250 million years ago. You can build up a stratigraphy of the biology. You can look at where there are more species and where there are fewer species. tying those two timescales together is really tricky because each of them has different error bars on them. So what I've been looking for is spikes in the element mercury in the sediments that record the biology. And that allows us to look at cause and effect in a much more detailed manner.
Mercury's quite a dangerous chemical, isn't it, if it's sort of in the atmosphere?
Absolutely. That's the sort of, one of the really interesting things for me anyways. I didn't start off studying mercury expecting it would take me to mass extinction events. No. I actually started off during my PhD considering how much mercury came out of volcanoes because it's a really important pollutant that we want to understand. It can bioaccumulate, it can cause various neurodegenerative problems and things like that. It's actually now regulated by the Minamata Convention of the UN. So I started off asking the question, how much mercury comes out of the world's volcanoes, because I was interested in what the natural background was that we were disturbing and against what backdrop we were operating in terms of trying to tackle mercury pollution issues. Yeah. So that's where I started off. I started off sitting in volcanic plumes measuring mercury. And just because this is how science works and it takes you off in exciting directions, then this suggested this idea about maybe we could use mercury signals hundreds of millions of years ago to tell us something about how our planet works.
Absolutely fascinating. I could talk to you for hours about this, but I'm conscious of your time. Getting on to your book, one which I'm really looking forward to reading. One of the in the preface, it sort of says something about the fact that you also talk about it to do with cultures and history of people and how they viewed volcanoes. Could you just tell us a little bit about that? Because I think that's equally interesting.
Oh, it's a very rich topic, and there's so many things to say. I mean, yeah. People who live close to active volcanoes, they take on meaning. Of course, they do. They're mountains. Mountains are special places in and of themselves. They're very visible to us. They can represent the sort of unattainable or the struggle to get there and things. And then you layer upon that the fact that you've got a capricious spirit, in a way, of the mountain in terms of the volcano that is smoking away. It has a different character every day. Sometimes it lashes out and is very destructive. And it can change on a really human timescale in a way that the more immutable mountains might not do. So there are many myths and legends and ways that people have tried to make sense of volcanoes in the past. So, I mean, this goes, the Romans had ideas of kind of gods or giants being trapped under the volcanoes, and the smoke was their kind of breath and things like that. And the earthquakes were them sort of pounding the ground with hammers, forging materials, all sorts of wonderful kind of imagery and things like that. And then, another wonderful example is the goddess Pele in Hawaii, who is still very important to their culture today. So when we went to work on Hawaii, it was very, very moving. We did a sort of ceremony to ask Pele's permission to work on her volcano. And there's lots of writings about the way that Pele arrived on the islands, and she seems to move from the older islands to the newer islands. And there's some imagery about Pele traveling underground from the volcano to the ocean. So she's supposed to live in Halabama, which is the summit caldera there, which is probably lava traveling through lava tubes and things like that. So there's wonderful, wonderful imagery like that. And I think many of the volcanoes you go to, there's some sort of spiritual way to make sense of them, as well as going there as a scientist and having a very sort of scientific approach to trying to read their moods.
And do you feel that when you're there?
Yes, yeah, I do. I think, as I said, I think and I respect them very much. And you must do, because you must remember that they're very, very they're incredibly powerful, and they're incredibly powerful spirits that must be treated as such. Yes. I understand the science behind them. Yeah. Or there's still many, many questions. Yeah. But I think it's important to acknowledge the force that's far more powerful than yourself.
I know that when you look at nature and you look at animals, I guess in time with earthquakes, animals would have been a good sort of if there was going to be an impending earthquake, you find that, birds would go off somewhere or something like that. Does the same thing happen with an impending volcano? Do animals react to something happening that's going to happen?
It's a bit similar to sort of the way that humans can sense it as well, I suppose, is that sometimes volcanoes have these long ramp-ups and you can become used to the small earthquakes that are happening or the changes in other ways that you might experience in the run-up to an eruption. So there's definitely profound impacts on vegetation and animals when you have an eruption itself. I think that's often watching the nature around volcanoes also very much fascinates me. So I think this comes out in the book a bit. I talk about bee colonies that I sit and listen to buzzing on the Messiah's crater rim, and these special bees that live there because I think predators are kind of minimised by the acidic gas plume. And then the wonderful accounts. It's a devastating eruption in 1902 in Guatemala. You get these wonderful accounts of the ants repopulating the volcanic devastation from some of the observers who went in there. So I think that volcanoes exist within a landscape and within biology. And I think I'm not a biologist by training at all, but I'm always very fascinated in how animals interacted with that.
One last question I've got is if there's any listeners that are interested in studying volcanoes or the earth sciences in general, what advice would you give them, Tamsin?
Well, if you can, get out into the landscape. As I said, there's some wonderful places to visit that are volcanically active and not too far from the UK. You could go to Iceland. Is always an amazing place to visit. It's an incredibly young landscape. It's being recreated all the time by its volcanism. Or the volcanoes in Italy or Greece are also fantastic places to visit. But if that's beyond budget or beyond timescale, as I said, go up and have a look at the north of the sky, look at these amazing layers, layer upon layer of basalt that you get up there, and wonder at the enormous forces that must have created that landscape.
Well, Tamsin, it's been a really fascinating conversation. It's been interesting to learn so much more about volcanoes. My guest today has been Tamsin Mather. Tamsin is Professor of Earth Sciences at the University of Oxford, and her first book, Adventures in Volcanoland, What Volcanoes Tell Us About the World and Ourselves, is out now. And you can find links to Tamsin and the book in the show notes. Thank you for coming on the show, Tamsin.
Oh, it's been an absolute pleasure.
You have been listening to Undercurrent Stories. I hope you enjoyed this episode. Please feel free to share the show link to your friends and family, and if you have 60 seconds, I would be most grateful if you would please rate and review. To hear more episodes, please subscribe to the show and visit undercurrentstories.com. If you leave your email in the link, we will notify you as soon as new episodes are released. Also, check out our social media links, details of which can be found on the show notes. Until next time, this is Bob Wells wishing you all the very best.